In this video, I'm going to talk about solving simple series circuits. A series circuit is like this one where you've got a source and then two or more loads all on one path so that all the electrons go through all the loads. To talk about how to solve these, I'm just going to assign numbers to this one and take you through it. This is your source, your battery, with your positive and negative terminals. By conventional current then rules, the current is coming that way out of the battery. And let's say this battery has a voltage of 10 volts. So the potential difference across here is 10 volts. We often use a 0 as a subscript for the source. And then here's our first load with a resistance of 2 ohms and our second load with a resistance of 3 ohms. So our goal here is going to be to find all the voltages, all the currents through this circuit. We're going to organize our solution in a chart. All right, and our chart has columns for the potential difference, the current, and the resistance. And we want those values through R1 and R2, and also for the circuit as a whole. So we'll say total for the last one. And let's make it look more chart-like. Yeah, just like that. Perfect. And the relationship between the potential, the current, and the resistance for each resistor and for the circuit as a whole is going to be Ohm's law, V equals I times R. So these are column headings, but also the elements in Ohm's law. Now, if you have read about series circuits at all, you have probably seen that if resistors are in a row like that, so that all the electrons travel through both resistors, then the total resistance of the circuit is given by this formula. The effective series resistance is R1 plus R2, and keep going for however many resistors you have in a row. And therefore, for this circuit, the total resistance is going to be 5 ohms. All right, so I'm going to write that in the chart. For the total for the circuit, the resistance is 5 ohms. Let's write in some other things in the chart because we've been given some other information. We know that the resistance of the first load is 2 ohms. And the resistance of the second load is 3 ohms. We're also given the potential of the source as 10 volts. That is the total voltage of the circuit, so that's going to go right there. Now, when we have our information organized in a chart like this, it's fairly easy to see what you can solve for next. In the last row, the total for the circuit, you know V and R, so you can find I by that relationship. So I is going to be 2 amps. This is a very economical way to set up a solution for a circuit. You could write down the formula umpteen times if you want to. I like the chart. It saves writing time. You're just going to be using Ohm's law over and over, really, and I don't think you need to write it down each time if you've got this relationship governing the top of your chart. Okay, next thing you need to know about series circuits. The current in the circuit goes round and round and round, okay. Starts at the source, goes through the 2 resistors, comes back to the source. The current is the same everywhere in the series circuit. Now, it's a misconception that, here because it's got all the potential, the current's really big, and then it loses energy through the first resistor. And it's true, it does. So it slows down, but it doesn't. And then again at the second resistor until it comes back here, just like crawling on its knees. That's not the case at all. The current stays the same everywhere. You may have noticed when you did the computer simulation for Ohm's law, you could see the little electrons going round and around the circuit, and they're all going together. The reason why they have to do that is because they are all negatively charged and they repel each other. So if you were to have fast places and slow places in the circuit, you would get them bunching up. And that just doesn't happen. They all need to be as far apart from each other as possible because of the electric repulsion, and therefore they will stay evenly spaced and go around at a constant rate. Okay, well that's good news, because with the current the same everywhere in the circuit, that means 2 amps, 2 amps. And now we're almost solved. Because of Ohm's law, we now know that the potential through the first resistor is going to be 2 amps times 2 ohms is 4 volts. And the voltage on the second one will be 6 volts. And you probably noticed there that adds up to 10 volts. That's another relationship for circuits. It's called Kirchhoff's voltage law, that the potential gained at the source will be lost at the loads, whatever path the electrons take. So if it's going to gain 10 volts here, it's going to lose a total of 10 volts through the loads that it passes through. And this is a lot like gravitational potential energy. Skiers on a hill, right? If you think of the source as the ski lift, it takes them up to the top of the hill, and they've got all this gravitational potential energy. They go down the hill and they come back to the bottom of the ski lift, and they've lost all that gravitational potential energy. Same idea here, but with electric potential energy. So that's a good check there, that the 4 volts and the 6 volts equals 10 volts. And now the circuit is solved. You know all the voltages, all the currents, all the resistances. So having done that, I'm going to do an example from the textbook. And this is number 29 from page 638. Your textbook likes to describe circuits and have you draw them. So that's the first thing we need to do. This one's a little bit different because you're not given all the resistances. Let's just go through this and get it set up. We've got 2 loads in series connected to a 75 volt battery. So it's similar to the last one. A battery and 2 loads. That's not right. And it doesn't matter where you draw these 2 loads, like they could be both here, they could be one here, one there. As long as they're all in the same line, it counts as a series circuit. Your battery, 75 volts. One of the loads is known to have a resistance of 48 ohms. Okay, so we'll say it's this one. So R1, 48 ohms. And if you measure the potential difference across this load, it's 40 volts. So let's write that down. The potential difference across this load is 40 volts. And the question is, what is the resistance of the second load? Okay, now my advice to you here is, whatever the question is, just assume you're solving everything in the circuit and set up one of these little charts. So remember, it's governed by Ohm's law. V equals I times R. And we need to know these values for R1 R2 and for the circuit as a whole, the total. So there we go. So what do we know here? We know the total voltage is going to be 75 volts, the battery. We know R1 and V1. And then we use the things we know about series circuits to start filling this in. And so everything else I'm going to do in a different color. Starting with the voltage relationship, this Kirchhoff's voltage law. Any potential gained at the source is lost in the loads. So the 75 volts here, the electrons go through both loads, lose 40 volts here, so the rest of the 75 volts must be lost through R2. So the voltage across R2 has to be 35 volts. Then you see across the first row, you have V and R, so you can find I. Something looks wrong there. It's because this R is 48 ohms. Okay. So you can calculate I using Ohm's law. I will equal V divided by R, and that value is 0.833 amps. Great. And now we can fill in the whole I column because we know that the current is the same everywhere in a series circuit. So 833 amps. And I mean the total current is the current through the source, 833 amps. And knowing those, now we can use Ohm's law again to find the final resistances. Okay, so R will be V divided by I, making this one 42 ohms. And then for the total resistance, well, you know the relationship for series resistors, they just add. So the total resistance of the circuit must be 90 ohms. And you can check that. Here, we will check using Ohm's law. Total resistance. The potential of the source over the total current. So just using that last row, 75 volts over 0.833 amps does give you 90 ohms. So you see you get 90 this way, you get 90 that way, and if you get to that point, you're sure you've done it right. Now, that's another good reason to just solve the whole circuit because it enables you to check your work. So what were we asked for anyway? Calculate the resistance of the second load. .42 ohms. So to review what's going on in series circuits, the main relationships here, Ohm's law applies to every resistor and for the circuit as a whole. The current is the same everywhere in a series circuit. And the voltages across the loads add up to the voltage of the source. That was so much fun. I'm going to do it again, but bigger. And so those are the relationships that will get you through series circuits. Oh, and the resistors. There you go. All these things are true. So those are pretty straightforward. Try a couple before you go on to the more complex circuits, and good luck.